One thing that is important to be able to do in statistics is to read computer output from statistical programs, because in real life statisticians aren't using a graphing calculator. They're going to be using computers to do their statistical data processing. So let's take a look at a couple of different statistical programs and how they would do a t-test or an interval. So this is the example from the coffee fill. So and these are from StatCrunch. I put the data into our StatCrunch program and did a hypothesis t-test and a t-interval. So here it shows mu is the mean of the variable and lists the variable as the coffee fill in ounces, which I typed in when I entered the data. It lists the null hypothesis as 10 and the alternate as less than 10. The sample mean is 9.845. The standard error, which is something I want to talk about, degree of freedom, the t-statistic, so this is our test statistic, and our p-value. So what exactly does standard error mean? In the book we talk about standard deviation refers to a population, whereas standard error refers to a sample. But when you're talking about computer output, standard error refers specifically to the distribution of the sample statistic. In other words, standard deviation would be the sample standard deviation, which in this case would be S of x. But when you see standard error, that's going to be S of x divided by the square root of n. So this has already been divided by the square root of the sample size, and the sample size is 20 because degree of freedom is 19. So this has already been divided. This is the value that I would use then to calculate my t-statistic. My t-statistic would be my sample mean, 9.845, divided by 10, which is the null hypothesis mean, and this would be divided by 0.04441, etc., the standard error, okay? And that would give me negative 3.49, and then the p-value, of course, would be the probability that t is, since this is a less than, t is less than negative 3.49 standard deviations from the mean. That would be 0.0012. Okay, so that's how you interpret all of that. Now, confidence interval, everything is the same, but it just gives the lower and the upper limits of the confidence interval. And of course, the sample mean would be right in the middle of these two values. So you could find the margin of error if you wanted to. The margin of error would just be the upper limit minus the sample mean, which would be right in the middle of the interval. Okay, this is an example of a paired t-test. So in this example, let's just say this was the average score on the pre and post quiz in a course. Okay, so actually no, that would probably not be a good example because that made it look like they did worse after than they did in the pre-test. Let's say this was maybe how many seconds it took to go through an obstacle course, and the pre-time was the first time they tried it, and then they did some training, and then this would be the post one. So the difference, which would be in this case post minus pre, is negative 8.65. So they on average improved their time by 8.65 seconds. So let's just say that's what it means. I don't really have a context for this. So when you do a paired t-test, then this one lists the sample size of 20, the standard deviation, and the standard error of the mean. So this would actually be 10.31 divided by the square root of 20, okay? And that does it for each of these values separately, but what I'm really interested for my test would be this part, would be the paired differences. So my standard error, my mean, my mu difference, so this would be my mu difference here, would be the negative 8.645. So the confidence interval for the mean difference, okay, is going to be negative 15.35, negative 1.95. Notice that would be right in the middle. The test of the mean difference would be the mean difference is 0. In other words, there's no difference between the post and the pre-times versus not 0. The t-value is negative negative 2.7, the p-value is 0.014. So we could reject the null hypothesis that there is no difference and say it does look like there is a difference, and in fact the difference looks like an improvement in the time that it took pre and post. Okay, then this next one is another paired samples test, but this is from a different program. This one was from a Minitab, by the way. This is from something called SSPS or SPSS. I can't remember which one it was, something like that. Notice here we don't see the separate, like the pre and post, we just see the mean of the paired differences. This would be our mu of our differences. This would be our standard error, and this would be our standard deviation. So this would be the standard deviation of the sample. So this would be S of x, and this would be S of x divided by the square root of the sample size. Well, the sample size, since the degree of freedom is 13, then the sample size, 12, then the sample size must be 13. No, here's our lower bound and our upper bound of our confidence interval. Notice the 4.6 minus would be right in the middle. This is the significance for a two-tailed test. This would be our p-value. So this is the way this program labels the p-value. Then we have one more. This is a test and a confidence interval for one proportion. I've done all means so far, so I wanted to look at a proportion one. So in this proportion here, we have a hypothesis test and a confidence interval in here. So this has p is 0.25, p is less than 0.25. This is our x and n. So p hat would be 27798 divided by 112561. Very large sample, a sample of 112,561. So that is equal to our sample p. Here's the p-value for the test. Notice we do not get a test statistic, but we could figure out the test statistic from the information we're given. And we're only given the upper bound of the 95% confidence interval. But if I know what my sample p is, okay, remember that p hat plus or minus the a margin of error gives me my confidence interval. So all I need to know is that if I know the upper bound, I subtract the p hat, then I would know the margin of error, and then I could just subtract the margin of error from the sample p to get the lower bound. So I could figure all of this out from the information given. So I wanted you to see some different examples. You'll see some other examples in the book and in some of the example problems where they ask you to interpret some computer printout from various statistics programs. And this is important to know how to read this.